In this presentation, I'm going to go through the relationships between position, velocity, and acceleration. It doesn't matter if we're in the linear world or the angular world. It just is the terms that we use in terms of angular position, angular velocity, angular acceleration, or linear position, linear velocity, or linear acceleration. The key, however, of what we are going to do is we are going to deal with one dimension at a time. That is, we'll deal with movement in the horizontal direction, or the vertical direction, or the medial lateral direction, each versus time, or in the rotational direction. And when we do that, we actually have some neat mathematical relationships that you can quickly pick up on uh, on these parameters as we understand them at a bit of a deeper level. So let's go through this. Right, so you should know right now position, velocity, and acceleration definitions, equations, and units. So position, we'll use displacement going forward because we want this to be a vector at this stage. It's the straight line distance between 2 points. In this presentation, I'm using delta S, final position minus initial position. And the units of displacement are any units of length. It's a vector, has magnitude and direction associated with it. Velocity, time rate of change of displacement, delta S over delta T. Units of length over units of time. Uh, and so meters per second, miles per hour, what have you. This is a vector as represented by magnitude and direction. In acceleration, time rate of change of velocity. Delta V over delta T is the equation, and units of velocity, the units are any units of velocity over any units of time. Now, clearly I could have put down angular position, angular velocity, angular acceleration, same relationship that we're going to be dealing with. I'm just going to stick with linear. So when we look at these three parameters, I like to understand these relationships not only as mathematical relationships, but also by graphing them out. And you'll often hear me refer to, or other people refer to, let's do a PVA sketch. And that what that means is we just sketch out our ideas in terms of the kinematics of a movement, the position, the velocity, and acceleration of an object during a particular period of time. So when we do this relationship, this PVA relationship, we are always going to stack our plots just like this: position on top, then velocity, and then acceleration. And what we have here is one dimension of position. So for example, this could be horizontal position during running versus time. This would then be horizontal velocity versus time and horizontal acceleration versus time of whatever object, running, walking of a person, what have you. Or this could be vertical position, vertical velocity, vertical acceleration, or medial lateral, what have you. Or it could be angular velocity, angular acceleration. But the key is that we're going to do one dimension at a time. And when we do that, we get some really neat mathematical relationships that our eye can pick up on as we graph out these different parameters. And what the other part that's really important is on these three plots, time is always going to be on the x-axis, and time will always be moving forward on the x-axis. All right, so time, time, and time. All right, so that's our plots. All right, so now let's just look at this. I just drew a simple description of some movement. Doesn't matter what the object is, sliding on a box, sliding on a table, it doesn't matter. And I've got, in this case, a position in that red line, and this would be the initial position, and this would be the final position because time is always going to be moving forward. So the final time will always be further to the right. The math of this is, well, let's think of this. I've got slope is positive, velocity is positive. So with slope, think about slopes and what slope represents. I'm sure you've all gone through slopes with some math class throughout high school or maybe even college. And slope tells us how steep this line is. And we also know slopes are either positive or negative. In this case, I've got a positive slope. If I drew the line down negatively, like that, that would be a negative slope. If I draw it just slightly up, that's less positive. This is more positive, and this is even more positive. Okay? Go back to my original. There you go. So the slope tells us the steepness of this line. Now let's think back to our equation for slope. And I'm sure you've heard the equation rise over run. Change in y, change on whatever's on the y-axis, over change in x, whatever's on the x-axis. If we look at this, this is our y-axis. And if we calculate our slope, we take the change in rise, the change in the y, which would be delta position, over the change in x, which is delta t. Well, that's our equation for velocity, rise over run. So if we look at this plot, the slope of the position versus time plot tells us everything we need to know about velocity versus time during that same time period. You don't even need to do any of the math. If this slope is positive, velocity has to be positive. If this slope is this steep, whatever the math is, that's how much velocity there is going to be. If there's less of a slope, there's going to be less velocity. If there's more slope, more steepness, there's going to be more velocity. And it would be the same time period that we're dealing with. So velocity represents the slope of the position versus time plot. Let me go back to my original. One too far. One too far. There we go. There we go. The steepness of this slope tells us the magnitude of velocity, and whether or not the slope is going up or down tells us the direction of the velocity. This is the beauty of doing one dimension at a time. So I put some numbers on here just for the sake of confirming this graphical understanding of this relationship between position and velocity. So here, if I've got the initial position as 1, that would be this position, and the final position is 2, if I come over here, that would be 1, this would be 2, and my initial time being 0, and my final time being 1 second, well, I can calculate my slope, I can calculate my velocity. Final minus initial, 2 minus 1, divided by final time minus initial time, 1 minus 0. That's a positive 1 meter per second. The positive sign indicates that this slope is positive. The 1 is the magnitude that tells us how steep that slope is. And now we've got our velocity, which I would put a 1 here, and that would represent 1 meter per second. All right, let's keep going. Here's another example. This is the negative slope. Right away, we should know velocity is negative. Now remember, when we're dealing with one dimension at a time, the negative sign of velocity is simply telling us which way movement is occurring. So movement is occurring in the negative direction. In the previous example, velocity is positive. All that means is velocity or movement is in the positive direction. So now this is in the negative direction. So let's put some numbers to it. Well, slope is negative, velocity will be negative. The initial position being 2, the final position being 1, the initial time being 0, and the final time being 1. So final minus initial divided by the change in time. That's negative 1 meter per second divided by 1 second. That's negative 1 meter per second for velocity. The negative sign indicates direction of movement, and it indicates that the slope is negative, and I drew that below the 0 line. If this was more negative, I'd have more negative velocity. If this was less negative, if this was less negative, I'd have less velocity, closer to 0, less steep. And I would just have to change my numbers there. All right. So calculating the slope of the position versus time plot tells me everything I need to know about velocity. Let's keep going. Well, what if the slope is 0 of position versus time? What does that tell us? It tells us velocity is 0. That means that the position is not changing. So whatever the position is initially, 2 meters, then the final position, if it's also 2 meters, the velocity is obviously going to be 0 meters per second. Change in position over change in time. If there's no change in position, then there's no velocity. The object is not moving, so velocity is 0. And it doesn't matter if I'm dealing with walking forward. It doesn't matter if I'm standing at the 2 meter mark or standing at the 1 meter mark. That's still 0 slope. That's still 0 velocity. I'm not moving. It doesn't matter where this line is. That's always going to be a 0 slope. Okay? So 0 slope on the position plot tells us 0 velocity, and that 0 velocity tells us we're not moving. So these go hand in hand. Whatever I plot up here, I get down here, and whatever I know down here, that also determines my position plot. Let's keep going. Now let's look at the next one. It's getting a little deeper though, and we gotta be careful. So now I've got velocity, and you notice I'm not gonna put position here, because I'm gonna try to keep this simple at this stage. So now the slope of the velocity plot is positive. Acceleration would be positive. Well, let's look at this. How do we calculate slope? Rise over run, change in y over change in x. In this case, change in y is velocity and change in x is time. That's the exact formula for acceleration. Delta v over delta t. So the slope of the velocity versus time plot tells us everything we need to know about acceleration. I've got a positive slope. I'm going to have a positive acceleration. If I have a less positive slope, I'm going to have less acceleration. If I have a more positive slope, I'm going to have more acceleration. All right, so whatever I'm doing up here is going to automatically change my acceleration. Let me go back to the beginning here. Well, let's just confirm that with math. So my initial velocity being 1 meter per second, my final velocity being 2 meters per second, my initial time being 0, my final time being 1 second, delta v, 2 minus 1 meters per second, divided by delta t, 1 minus 0 seconds, is a positive 1 meter per second every second. That's what I'm drawing right here. That positive 1 meters per second tells us how fast velocity is changing. It tells us how steep the slope is. Again, if I make a steeper slope here, that acceleration number is going to be a greater value, greater magnitude. All right, so 1 meter per second tells us the slope of the object, of the velocity versus time plot is 1 magnitude. So here, if I'm dealing with something moving forward or backwards, now I would say in words, if this was an object, moving either forward or backwards, this is a positive velocity, meaning that that's going to be forward movement. And we know the magnitude of velocity is getting greater. It's going from 1 to 2. So we would say velocity is speeding up while the object is moving forward. It's speeding up. It's going from 1 meter per second to 2 meters per second. And velocities are all positive, therefore it's moving in the forward direction for that one dimension, if that's what we're dealing with. All right, let's keep going. Let's look at this one. Look at that. That's still positive slope. If that's a positive slope, what does that tell us about acceleration? It tells us acceleration has to be positive. That's the same positive acceleration as right here, because I just moved that line down. All I did is I dragged it down here like that. All right, there it is. It's the same slope. It's the same magnitude of acceleration. Let's do the math here, just to double check, make sure this isn't something weird. This is going to be that velocity, and this would be the final velocity, and be that velocity. Here's 0. So these negative numbers are going from -1, -2, -3, so forth. So this initial velocity is -2 meters per second. The final velocity is -1 meter per second. And the change in time I'm still doing is 1 second because it's easy math. Let's calculate our slope. Delta y over delta t, rise over run, change in velocity over change in time. Final velocity, negative 1 meter per second, minus initial velocity, negative 2 meters per second. So it's negative 1 meters per second plus 2 meters per second, divided by the change in time, which is 1 second. And we get a positive acceleration of 1 meter per second per second. That's the same positive acceleration as here, because it's the same slope. The steepness of the velocity versus time plot tells us the magnitude and the direction of the acceleration vector. Now notice I said acceleration vector. It doesn't mean the direction of movement is one direction or the other when we get down to this parameter. And notice that it doesn't matter where this line is. I could move it anywhere in here. And anytime I do that math, I'm going to get 1 meter per second per second. Anytime, as long as I draw a parallel line. So what does this mean kinematically? Well, again, it depends on what's on this y-axis. But if we're doing horizontal motion, well, now what's happening is velocity is slowing down. We're going from 2 to 1 meters per second in the negative direction. All right, so now velocity is slowing down while the object is moving backwards, the negative direction. So if I'm in my car, I got the car in reverse gear, and I'm stepping on the brake pedal. I'm slowing down while moving backwards. Okay? Now, this one was speeding up, moving forwards. Same acceleration, same acceleration. So what's the difference? The difference is the direction of the velocity, where velocity is. The steepness of the slope is exactly the same between these two. All that's changing is whether or not velocity is negative or positive. And that changes the entire interpretation. That's why for acceleration, if I'm only given acceleration information and that's all I know, I can't say exactly what's happening kinematically. Let's say there's a projectile, negative 9.8 meters per second every second. Negative 9.8 meters per second squared is the vertical acceleration. Can you, with any confidence, tell me that the object is moving upwards and slowing down or speeding up and moving downwards? You can't. It's the same acceleration. All right, so the direction of the acceleration vector does not tell us direction of motion. The direction of the velocity vector and the direction of the position vector does tell us direction of motion when we're dealing with one dimension at a time. All right, let's keep going. Oh, here's another one. Negative slope, acceleration has to be negative. Let's do the math. Initial velocity being 2 meters per second, final velocity 1 meter per second, change in time is still 1 second. So final 1 meters per second minus initial 2 meters per second divided by 1 second is negative 1 meter per second per second. That's the steepness of that slope. That's the direction of that slope. It's negative. It's a negative slope, and its magnitude is 1. And what we're going to see, it doesn't matter where I put this line. It's still going to be negative 1 meter per second, anytime that line is parallel to each other. In this case, we have positive velocities, and if we're dealing with horizontal movement, then that means the object is slowing down. We're going from 2 meters per second to 1 meter per second, while moving in the forward direction because I'm in the positive velocity range here. So now this negative 1 meter per second means slowing down, moving forwards. Let's go to the next one. Same slope, I just moved it downwards. Same acceleration. Let's just check our math. Negative 1 meter per second, negative 2 meters per second, 1 second of delta t. Final minus initial, so negative 2 meters per second plus 1 meter per second divided by 1, negative 1 meter per second per second. Same acceleration, same rate of change of velocity, same slope. All that's changing here is the velocities are either in the negative region or in the positive region. So now what's happening? Well, velocity, the magnitude is going from 1 to 2. The direction is negative. So now we have speeding up while moving backwards. If I'm in my car, I've got this in reverse gear, stepping on the gas pedal. I'm going from 0 miles per hour, 10 miles per hour, 20 miles per hour backwards. Reverse gear is telling me it's negative velocity. All right, so, all right, so same acceleration, but if I only give you the acceleration information, I don't give you any velocity information. All you can say for that negative acceleration is that's the direction of the acceleration vector. That negative acceleration, same acceleration, does not tell us direction of movement. This is forward movement, this is backwards movement. But hopefully now you see this relationship between these two is simply about the slope of the velocity versus time plot determines the acceleration magnitude and direction vector, direction of the vector. All right, let's complete our journey here. What if the velocity is constant? What happens to acceleration? Well, what's that slope? That slope is 0. Acceleration has to be 0. Final initial velocity is 2 meters per second. Final velocity 2 meters per second. Final minus initial divided by 1 second, change in time. That's 0 meters per second squared. What does 0 meters per second squared mean? What does 0 acceleration mean? All it means is velocity is constant. And it does not mean no movement. All right. It may mean no movement, but that's not what it means. It means velocity is constant. So this is constant and positive. This is constant and negative, meaning that you're moving backwards at a negative velocity, constant velocity. And here, this is constant and velocity is negative or 0, meaning now the acceleration is 0, meaning and that would be no movement. But that's just a special case. If velocity is constant, acceleration has to be 0. That's all 0 acceleration tells us, is velocity is constant. Do it again. All right? So as long as velocity is constant, it doesn't matter if it's negative or positive here, acceleration would be 0. All right, so the whole idea of this presentation is just to get this understanding of the relationship between slope of each parameter and what it means for the next parameter down. What we're actually doing is some pretty high level math. This is called taking the derivatives. So if we take the derivative of the position versus time plot, we get velocity versus time. If we take the derivative of the velocity versus time plot, we get the acceleration versus time. Another math term that we're also doing here is integral. If we take the integral of the acceleration versus time plot, we determine velocity versus time. And if we take the integral of the velocity versus time, we get the position versus time. So there's a lot of math behind this, but if you can pick up the relationship between the slope and the next parameter down, you're really moving yourself forward. So the slope of the position versus time plot determines velocity. The slope of the velocity versus time plot determines its acceleration. Direction of acceleration only tells you the direction of the slope of the velocity versus time plot. It does not tell you direction of movement. The direction of movement we get by looking at the direction of the velocity vector or the position vector, the displacement vector. But the direction of the acceleration vector does not tell us direction of motion. We actually need some more information to be able to say what's happening kinematically. All right, so hopefully this helps you see the relationships between position, velocity, and acceleration. And as you do, hopefully these plots start to make a little bit more sense. I know this looks a little bit messy, but I've got several videos on linking position, velocity, and acceleration for different movements, and then taking that acceleration for some movements, and then trying to understand something like ground reaction force because F equals ma. But if you look at this plot or look at these other videos and you see these plots PVA, you will hopefully start trying to pick up what direction is the velocity vector in this region. You see it's negative. What direction is velocity in this region? Hopefully you see that's all positive velocities. And then going down here, if you can pick up this is negative slope here. That means it's going to be a negative acceleration. This is all positive slope. That means this is all going to be positive acceleration. A little bit of negative slope here, meaning negative acceleration. If you can at least start picking up on some of the directions of the slope and what that means for the next parameter, you're doing really good. Okay, I hope this helps. Thank you.